Yes, hello everyone. My name is Mufava Dennis, and I'm going to take you through this paper I reviewed. It's decoding the protein ligand interactions using parallel graph neural networks. It was written by the people below and released in 2022. Well, PLI is crucial for understanding biochemical functionality and estimating biophysical properties essential for drug design. I think this must be a concept in biology where we're going to look at PLIs in relation to drug design. However, experimental characterization of PLIs is time consuming. So computation methods relying on 2D protein sequences data have limitations, and basically they have initially they had used 2D protein sequence data. So this paper aims at finding better means of estimating the biophysical properties of essential that are essential for drug design using PLIs. So we shall move on and look at the problem statement. Before we have an evaluation was made whereby they chose to work with parallel graph neural networks, of which it has two models that are basically talked about in this paper, which is graph neural networks for featureization and graph neural networks for proteins. So, we are going to look at, they look at statistics where they gave 0.97 to GNNF and 0.958 to GNNP. So I will talk about this further in my discussion. So basically looking at the problem statement to this paper, basically the paper revolves around the challenge of accurately predicting PLIs, which are crucial for rational therapeutic design in the drug discovery. So despite the potency of PLIs, there are challenges that are experience. So it's what we're going to look at here. Experimental characterization of experimental characterization is time consuming. Then it was also labor intensive. So the existing computation methods, particularly, were reliant on 2D protein sequencing data and we are limited in their accuracy and efficiency. So basically looking at these problems, they try to find solutions to that, which I'm going to take you through as well. So the methods they used first was network architecture. Here, the graph neural network architecture is defined to predict characteristics of protein ligand pairs by learning features of the protein and the ligand. So the molecular graph structure is defined as GI, you open those brackets, where we have V, comma, E and A, where V is the atomic node set, E is the edge set, and A is the adjacency matrix. So breaking it down further, we looked at it in form of the GNNF and the GNNP, which I'm discussing down, starting with the GNNF, which is a graph neural network with featureization as a model. Basically here they combine proteins and ligand adjacency matrices into a single matrix. So this utilizes docking simulations to obtain the protein ligand interactions, which are PLIs, to create combined features and adjacency matrix. So this employs a joint feature matrix for ligand and proteins in a tension ahead, which I'm going to look at down with a structure. So followed by two gut layers with with the subtraction step in the final attention ahead. Rather, in the final attention head, So I'm going to look at it in the picture in our illustration here, where they say the KNF uses the PLI obtained from the docking simulations to create a combined feature, which is this adjacency matrix, which is with subtraction, as we talked here. Uh, it's followed by two GAT layers with a subtraction step in the final attention head, which is what we are talking about here. So basically that's it with GNNF. Basically, this structure is called the GNNF attention head. So shall also look at the GNP, which is a graph neural networks for proteins as a model. So this one also separates proteins and ligand features and adjacency matrices. So it embeds proteins and ligand structures separately based on their adjacency matrices. So this employs individual GAT, which is a graph attention network layers for proteins and ligand features, followed by concatenation in the final attention head. So I will also share with you the attention head for GNNP. So here, basically, the features in the ligand and target proteins are coded separately alongside with their corresponding adjacency matrices. Yes, which is what they're talking about here in this diagram. So next we shall have the other methods that are used, the other node features, where each node is given a set of features engineered with emphasis towards biochemical information using the RD kit. Then we have dataset preparation, where two public datasets, the DUDE and the DUB bind, are used to train the models. Basically, that's it with the methods used. So we have we have regression model data sets where regression models are trained to predict experimental binding affinities, which is the EBA and the PIC50 values. So we have the hyperparameter optimization, where the hyperparameters such as network depth, layer dimensions, and learning rates are optimized through through experimentation. So we look at our dataset preparation. We have remember we talked about DUDE dataset and PDB bind dataset. So these two datasets are prepared to be used. So we have a classification of model datasets. First, we shall look at the DUDE dataset, where it consists of experimentally verified activity complexes and matched inactive pairs. So these datasets are designed to test molecular docking programs, but suffers from a limited chemical space and biases. So ligands and ChemEBL datasets labeled as positive, while the generated decoys considered negative. So we further look at the ligands labeled as active and inactive based on they are labeled. The ligands are labeled as active and inactive based on the docking poses. So too, we have the PDB bind dataset, which contains experimentally verified protein ligand complexes from the protein data bank. So these binding poses, binding poses generated by docking calculations, which are there down below. So we also have SARS or SARS COV2 dataset. This dataset comprises of 7 protein targets which relate to the SARS-CoV-2 viral life cycle. Then we have the IBS dataset, which was created using 486,232 synthetic compounds from the IB screening database. So we further look at regression model datasets. So here we discuss the datasets used for regression models, noting that these datasets are created from the same source using the classification model. So here we have the first as experimental binding affinity, which is the EBA prediction. This one utilizes datasets from PDB that we looked up that we looked at here. Then it also utilizes first, let's look at the PDB binding 2016, 2018, and 2019. So here, crystal poses from PDB 2016 used, including general, refined, and core sets. Then basically, decoy is labeled from experimental affinity of corresponding crystal structure. So basically, what they are talking about here is explained in this graph down here. In that the PDB of 20, which is PDB bind 2018 dataset splits into docked and crystal structures for the independent instruments. So then PDB 2019 dataset comprises of the target added after target added after 2016 with GDC similarly less than 65% of the training target. So experimental binding affinity, which is the EBA, estimated in terms of the KI and KD with labels defined as log KI slash KD, which I'm going to explain, which is explained down here in this the four graphs that we have here. So we have graph A, graph B, graph C, and graph D, where graph A is MPRO, NSP 15 IBS as graph B, then MPRO down, which is active and inactive. So basically here they talk about the graphs A and B that correspond to the predicted binding probability of NSP15 and the MPRO in the IBS molecules, which is up here, and then C and D graphs correspond to the predicted binding probability of active molecules from the MPRO and the NSP respectively. Which is active and inactive, which is the graph C and graph D, which is MPRO active and NSP15 actives. Sorry, I said inactive, but it's also active. So the graph this side talks about these molecules being predicted binding probability for the MPROs, and then that here down the MPROs are active, which are and vice and which is the same for this side, where we have the NSPI, which also correspond to the predicted binding probability, and below is the NSPI 15, which are active. So we further look at the IP in the PIC 50 prediction. So this one focuses on estimating the potency of therapeutic candidates towards protein targets. So PIC 50 calculated as the inverse log of the half maximal inhibitory concentration. So the combination of DUD and PDU and basically the combination of DUDE and PDB binding 2016 data center are used. So the results of we have results and the discussion. So we look at the graph neural network classification models where they aim to predict protein ligand interactions with a high accuracy. Training on datasets with varying numbers and targets and complexes. Targets shown that increasing the dataset size generally improves the accuracy. Then we look at general applicability of these data sets. Well, test sets with varying similarities to the training set were used to access generalizability. Then our GNNF model showed that consistently high accuracy across different test sets, indicating good general applicability. However, um, excuse me, GNNP models accuracy vary more. So basically here they're trying to compare GNNF and GNNP. So you have the top N ranks where we have the graph neural network models outperformed docking in identifying top scoring poses of protein ligand complexes from training data. However, these performances vary on test data as well. So we go to performance on the different data sets. Well, we tested data, rather I won't say we because I'm reviewing what they did. They tested data sets including molecules from the ChemBL and SARS-CoV-2, where GNNP performed best for this data, but struggled with this due to the significant dissimilarity from training data. And then we look at binding probability distribution. Here, GNNP showed better performance in identifying potential binding affinities from NSP15 target compared to the MPRO target. So yeah, and in the aspect of graph neural networks as a regression model, GNN models were modified. Sorry, they were modified to perform regression for predicting binding affinities. So the evaluation of various datasets shows competitive performance compared to existing deep learning methods. So we looked at ISP, rather PIC50 regression experiments, then a prediction of inhibitors for Kosovo's MPRO. So in conclusion, the target Sabinovo graph-based deep learning model, which is the GNNP and GNNF for PLI's prediction. Here, these models achieve high accuracy of 0.99 compared to the 2D methods used, and they outperform existing models in predicting binding affinities and PIC50 values. So in all the study that we've done here, I looked at a few keynotes that we can take out from this paper. One, we have the GNN and the GNP leverage 3D structure data of proteins and ligands to predict PLI. Then two, the models can also be used to classify, used in classification and regression. Then GNP performs well even without docking information. So basically GNP is the best option to use. Then the approach is particularly useful in early drug discovery stages for virtual screening of large ligand libraries. And lastly, the study paves way for generalizable models incorporating various data sources for improved PLI prediction. And lastly, what we've been looking at in the entire book or in the entire article that I was given to review, basically we end up looking at the different. Here on the left we have the inputs, the proteins and the ligands. Sorry. Then we have their activation. Then what we end up with, either in the classification or in the regression. So basically, in a nutshell, schematic showing the schematic here in this illustration shows the results produced by each method in both regression and classification model. So the inclusion of a 3D structural data provides numerous advantages and abilities to produce such a range of prediction, both active and biophysical properties. So their relationship with the protein, which is their, sorry, which is their relationship with protein ligand interactions. Basically, it's what we're talking about here. We have the inputs, which are the proteins and the ligands. Then we have the activation. Then we have the classification and the regression. Basically, that's it. That was it with that was it with the paper I was given to review. Thank you so much. I remain Mukwaba Dennis, student of computer science, year 2, Makerere University. Thank you.